think I'm going to jump right into it. Thank you, everybody, for coming this morning. I've got a lot of material to cover, so we will just get started here. And I'll begin. Thank you, Bree, for that introduction. I've been doing hydrogeology and stormwater infiltration design for over 20 years now, and I'm looking forward to sharing some of the things I've seen as an owner of our geotechnical company and as doing design and construction work for land use applications and as part of municipal review. So, you know, what we see over and over again is that, you know, the post-construction reality is that infiltration systems, you know, once they're designed and built, they're pretty much ignored until they become a nuisance. And so the goal here is to identify those key things that will improve the long-term performance of infiltration facilities and reduce operations and maintenance load. So plan review, this is the key opportunity to cross-check geotechnical and civil design elements and look for disconnects before construction and then during construction. Our role as the geotech on a project is to help the civil with that subsurface plumbing, to understand where the water goes, and that's the hydrogeology or the groundwater flow paths, the vertical infiltration rate, not just the lateral sideways flow rate, but the vertical. And you know, fundamentally poor characterization, a change in subsurface condition, or poor assumptions, no oversight or very little oversight during construction, just equals maintenance issues. So I'll give you the answers right now. The theme here is inadequate subsurface characterization, testing and design, the lack of oversight, and then issues during construction. That's almost all of the reasons we see for facilities failing. If we can pay attention to the upfront design work, pay attention during construction, make sure that the TSC plan is followed and the water quality treatment elements work, your facilities are just going to last a long time. Good conservative design results in good performing facilities. Okay, I'm going to go through what a geotech report should include, some key plan review elements, and then if there's time, I'm going to run through a series of examples. And I can't see the chat, and so when I'm running low on time, please chime in and let me know. So geotech reports should all include this basic information. What is the receptor soil? What are we putting the water into? Needs to have an interpretation. Someone needs to assign a geologic unit to that soil. Discussion of the presence or absence of stratification, the layering. Is the soil consistently sandy gravel, or is it full of silty inner beds? That needs to be described in the geotech report and on the soils logs. When infiltration testing is conducted, it should represent vertical flow paths for infiltration ponds and bioretention facilities. That's how those depend. The stormwater models all assume that the water put into those ponds is soaking vertically downward. The depth to groundwater needs to be identified, whether there's an aquitard, and which direction is groundwater flowing. These are all fundamental things that should be in the geotech report. The reason why is kind of illustrated with this little cartoon from University of Minnesota showing a pond next to a foundation. In this image, you see bedrock there, the dark gray unit. For our neck of the woods, glacial till is also usually considered an aquitard, a barrier to vertical flow. So the geotech report should talk about the thickness and lateral extent of the unit we're putting the water into. And there should be separation from perching layers and from the water table. This is This is more of a terminology slide. You see a cartoon of outwash, till, and outwash again. So in the Puget Sound area, you will see these terms used over and over again in geotech reports: recessional outwash, glacial till, and advance outwash. And at depth, beneath those three Vashon age deposits are either transitional glacial lake deposits or older non-glacial deposits. The take home here is that outwash is an excellent place to put stormwater, treated stormwater. Glacial till typically is a barrier to vertical flow and can be really challenging to infiltrate onto. This image here is showing a landslide deposit from Ecology's landslide hazards website. But most uplands in the Puget Sound area, they're capped with a layer of glacial till, and many times there's a thick advance outwash sequence underneath the till. Infiltration can work really well when you can dig through the till and put it into the outwash, but the infiltration applications have to address the potential for impacts. And this one is illustrating landslides. A lot of our landslides along Puget Sound form at this geologic contact between advanced outwash and older transitional beds or Lawton clay or fine-grained units. Glacial till, I'll just spend a minute on this one because this is important to your surface water model and to an infiltration study. Glacial till was formed at the base of the ice sheet. It typically is referenced in manuals as a source material for building earthen dams because the matrix is a silty fine sand. And when you compact that, it does an excellent job at holding water in. In the natural condition, there's a thick weathered horizon. A nice alderwood soil series forms that is like a sponge in the undeveloped condition. But in the urbanizing area or suburban area, much of that weathered horizon has been removed, and you're right on top of the hard unweathered till. Regional studies by USGS estimate that the recharge rate through glacial till is about 1 to 2 inches a month. So when you put facilities on top of that unit, the water is mostly moving sideways. So when geotechs approach a site or they're asked to go explore a site, it's usually 2 different phases. Many times there's a feasibility phase where someone wants to do something with the site and they need to get a sense of the critical areas, the basic soil properties for foundations and for infiltration. There may not be an infiltration location identified. Then once that initial feasibility report is done, the civil and the architect put together the proposed land use, and then a second phase of work is often conducted specific to an infiltration facility. And that infiltration specific geotech report should cover all of these items. There should be exploration specific to a facility, infiltration testing or soil sampling at the facility base. The groundwater should be identified to the depth to groundwater and whether or not the seasonal high can be estimated with the information. Which way is the groundwater flowing, particularly for shallow groundwater settings? And once that water soaks into the ground, where is it going? What is the fate of that water? On the design side, the design infiltration rate needs to reflect the density of subsurface information, the size of the drainage area, the ability of the owner to conduct maintenance, and the ability of the facility to be maintained. We see a large push toward underground infiltration facilities, and those maintenance of those hasn't been well documented in terms of actually fixing a serious decline. It's easier with open ponds where you can see the problem. I'm going to go through some of those elements. So subsurface documentation, the exploration data relative to the facility location. This is an image of a geologic cross-section, and the vertical profile with the geologic layers, and these vertical lines here are the exploration locations. Some mapping or soils log should be included that give you a picture of what the subsurface looks like relative to the facilities. These rectangles are future infiltration vaults. The groundwater should be identified. Here, there wasn't groundwater encountered, it was dry. And so there needs to be a basis for assuming groundwater. Distant locations found the groundwater table, and how does that relate to different facility locations? For the design infiltration rates, just a little bit of history. Earlier requirements in the 80s and 90s were based on the septic design world, small footprint, small volume tests. They did not represent the subsurface very well, and there was very impressive failures in the 1990s. And King County stormwater manuals really changed starting in the mid-90s. The requirements became more robust. The type of testing changed to encourage larger tests that had more water. This little quote here by Carl Terzaghi is so apt. Soils are variability. They vary both laterally and vertically. And the way we understand that is understanding how they're deposited and whether or not a test in one area represents the permeability in a different area. A key reason why sometimes infiltration tests do not represent the subsurface is due to just natural subsurface variability, stratification, the layering of soils tied back to how they were deposited. If we're testing above a silty sand, we're going to get a lower rate. If we're below the silty sand, we may get a higher infiltration rate. And so the natural layering of soils should be discussed relative to the infiltration test results. One of the key things I look for when I'm reviewing the test is, do they provide any background for the infiltration test? Do they provide the amount of water that they used and how long they ran the soaking period? Did they just fill it up and go away, or did they hold it constant? Did they report the volume? Another important piece, particularly for large facilities, is, will a mound build up underneath the facility? A permanent groundwater mound. And does that change the performance infiltration rate? And does it impact adjacent infrastructure like a wall or a slope or a basement? These things need to be called out in the geotech report. And then a different type of a way to estimate infiltration rate is based on grain size. This is not a water in the ground test. This is taking a sample and running it through a mechanical shaker and measuring the size of material retained. It is not the same as putting water in the ground. Grain size can be a low-cost way to get a gross estimate of infiltration, but the caveat is it takes away any stratification. And for certain grain sizes, it just can really miss. What we have noticed by comparing grain size tests to pilot infiltration tests, when we run a pilot infiltration test and then sieve the material that the water moved through, when we have very gravelly soils, the grain size based equation can give you a higher number. And when we have silty sediment, the grain size based equation can give you a higher number. It works really well, relatively well, for medium grain sand. And so just as a quick review, the geotech report should go through those basics: the subsurface characterization, how they collected the data, how thick is the layer we're putting the water into, and what was the basis for the infiltration rate and the seasonal high groundwater. And ideally, there's a geologic cross-section that shows the subsurface layers, where the facility is, and where that infiltrated water will go. Recommendations in the geotech are really important to see if they're carried through onto the civil design plans. This is just a list of some of the recommendations that we might make as part of a report. So plan review. Plan review reduces risk. Many times as a geotech, we're asked to predict the future. We do not have X-ray vision and we don't have any crystal balls. We have a few widely spaced explorations that we are correlating between. And so the quality of the data is really important. If there was poor recovery or the driller wasn't able to get to the certain depth because of refusal, that all increases risk. And so plan review from someone working for the owner, the goal is to reduce risk. For someone doing a review for the city, it's to reduce risk to the city. So the first cut that I would do is I compare the drainage report, the civil stormwater plan, to what's in the geotech report. And I look for big disconnects. Is the drainage report soils, are they calling out the soil type C, but the infiltration box is checked? That's a disconnect to me, because soil type C is usually a low permeability unit. So then I go to the geotech report and I try to see how they came up with an infiltration rate. Another big disconnect is there might be infiltrating permeable pavement, but the site is importing fill. These are just disconnects. On that soil class issue, in the drainage report, there's the surface water model that looks at the surface soils. So as a geologist, soils to us are just a weathered version of the natural geologic unit. And so a type A soil is usually an outwash-based soil, Everett, Indianola, Spanaway. A type C soil is usually a till-based soil, like an alderwood. And so it's good to get familiar with the terminology. The next check I do is I look at where the facilities are located relative to the infiltration explorations. Are they in the footprint? Are they at the right elevation or depth? Did the explorations find similar material, or was one different? And then does the grading plan remove the tested horizon? Are utility trenches going through the bioretention cell? I've seen that more often than not. And what are they backfilled with? And are there lateral check dams? Some of the other cross checks are those geotech recommendations. Are they showing up on the plans? So the depth for stripping, scarification, can the machine work in the facility? No, all of that needs to be called out on the plan. Further on a more detailed review is constructability and sequencing. Are the facilities in an area that access will be challenging to? Are cuts required near a building or a property line to install a vault? On the mismatch, some of the older bioretention designs still have fabric called out beneath the bioretention soil on top of drain rock. The fabric is a clogging interface, and we've really tried to work to remove those from the details and instead use a different material for the underdrain. Is there an overflow path identified? And number one for me is geotech field observation required during construction? So do your plan review. And this is just a review of what I've just gone through and highlighted here. Number one is there ground truthing required? I think we've got a little bit of time. We've got about 5 minutes here to do some case studies. So we were part of a team that worked with the Stormwater Action Monitoring Group at Ecology, funded by the Phase 1, Phase 2s. And we were looking at the hydrologic performance of bioretention. So as part of that team, I reviewed a lot of geotech and drainage reports. And the key disconnect I saw over and over again, especially with the first phase, was the stormwater drainage report not taking into account some of the geotech data. And that improved a lot with the second round, but be familiar with the model inputs. Take that WWHM training if you can, and look for, box checking so that the model input for the native soil infiltration rate should match the geotech infiltration test rate. Site variability. This was an elementary school. Till upland, underlain by advance outwash. We did several borings for foundations. We did test pits for a large infiltration vault. We did site-specific infiltration testing in the outwash. And then for water quality treatment and flow control, there was a series of bioretention cells. One of those bioretention cells had the underdrain taken out because for whatever reason, they couldn't get the grades to work. And the civil just included a note for geotech observation at the time of construction. That's a great note, but there wasn't a backup plan, and we didn't have any explorations in the footprint of that facility. And so during construction, glacial till was encountered, and we were lucky in that we could do test pits at the time of construction, and we found that the till layer was thin enough that we could dig through it. And so the civil did a field fix where they designed an infiltration trench underneath the bioretention soil. And so this was, it was identified early on that there was variability across the site, and that, there should have been another round of exploration to make sure it was okay to remove that underdrain. Another example of site variability. This was a project where we were called in to fix a poorly performing pond. The work by others had done some test pits and infiltration tests in the pond location, and one of those tests had a 0 infiltration rate. We don't know if geotech observation occurred at the time of construction, but we watched water levels in the pond for a year, and in the summer, when it finally dried up enough, we went in and looked at the subgrade, and half of the pond was built basically on a silty interbed and had an effective 0 rate. And so the solution was to pothole, install a bunch of shallow infiltration trenches to get through that interbed layer. And so on the review side, when you've got 1 0 test and 2 positive tests, that should be a flag to make sure that we're out there during construction to look for potential issues. Some photos from that site. Large pond for a residential plat. This was from, I think, the mid-2000s. For any facility, a very important element is the function of the water quality treatment system. And it's particularly important when your infiltration system is a UIC well. They're small diameter, and they work best when the water, of course, is as clean as it can be. For this site, the treatment system was a series of filter cartridges and bioswales. This particular case changed our approach to how we think about those filter vaults. We now require, as part of our plans and specs, we make the contractor run water through them before it's brought online. On this site, the bypass weir was set too low, and so none of the water was going through the filter cartridges. The site, strike number 2 is they didn't stabilize the site before they brought the wells online. Everybody's always pushing on school projects to get them online so the kids can start going. They want to get their occupancy. This one, the landscaping hadn't been fully stabilized, and so the first slug of water bypassed the filter cartridges, and it was chocolate milk, and it clogged the wells. So we went through an extensive cleaning process. Since that job, we've tested it, had the field test on other vaults, and on one of them, the cartridges were upside down. On another one, the cartridges didn't engage. And so it just raised our nervous level with these. For this one, it was a great way to test out cleaning techniques for UIC wells, and the wells They were cleaned and repaired, monitored for 2 years, and continued to perform well. And so the cleaning was successful. It just is always disappointing to see that setback for, you know, poor installation on this one. Let's see, how are we doing on time? This is a nice case study for plan review. This would have been an opportunity to catch this during plan review. It was a till mantled site. The testing was done in the weathered till horizon, which was then removed by grading. And so that one we should have been able to pick up on. Then during construction, the bioretention cells were excavated into till. This is a case history I've shared before, but it's a wonderful example of why till does really good for detention ponds when the weathered horizon is gone. So beautiful bioretention soil, nicely sloped, not planted because someone noticed that there were some issues. And then in the end, it made for a beautiful detention pond, had a little bit of lateral flow toward a neighboring lawn. And it's just one of those disconnects. You know, it's a type C soil. The weathered horizon was removed, and there shouldn't have been an expectation that it would work. Seasonal high groundwater is another one that we see challenging to get right sometimes. This was a project where we monitored groundwater for 2 years, thought we had a good handle on where seasonal high was. There wasn't a lot of space above the water table. We had a vault designed with the 3 feet of clearance, ran the groundwater flow model, everything penciled out. Then there was a late design change because of a utility crossing. Civil needed to shift the vault. We found out about it later, and the area that they moved it to, groundwater was a foot higher. So then we didn't have our 3 feet of separation anymore. And so when we're reviewing infiltration designs, one of the things I look for is the basis for the seasonal high groundwater. I think I'm getting a lot of blinking lights on my chat stuff, so I think I'm probably going to hold off here and go straight to the summary, leave that up. And then Bree, let me know, what do we do now? Is it open question?
We got 1 minute, so you can do your summary real quickly, and then if you have any questions for Jennifer, you can contact her. Her contact information can be found in the program.
Well, I'll just thank everybody for attending. I think sharing examples of where things go right and things go wrong is how we will improve our profession. I think we really need to improve site characterization, and I think we have. Over the last stormwater manual really emphasized the importance of subsurface characterization and testing, and I just want us to keep moving forward. Thanks, everybody. So on the chat, Spree, will they send me these questions so I can answer, or?
Yeah, if they have, just because we ran out of time, if they have any questions, they can directly email you.
Okay, super.
Thanks, Jennifer.
Thanks again, everybody.